Hi there, welcome to your lesson on standardizing distributions. In the last video, we looked at what a standard normal distribution is. In this video, we'll look at how we take a normal distribution and convert it into a standard normal distribution. Let's get started. And let's begin again by kind of recapping what a normal distribution is. When we have data that's distributed in a way where it's clustered around the mean and then has fewer and fewer data values as you go away from the mean, that's called a standard normal or normal distribution. Okay, so now we're going to look at the process of changing from a normal distribution, which has a mean given here and a variance. Here's the mean, here's our variance of 20 here, or sorry, standard deviation of 20. And we're going to take a look at how we standardize it. That means we take it from that to a normal distribution. A standard normal distribution looks like this. We use z to represent it. It has a mean of 0 and a variance of 1. So how do we do that? Again, the process is called standardizing. There's our normal distribution. There's our standard normal. Let's take a look how we do it. And in our last video, we tackled this curve a lot. We talked about these, and they're called z-scores, and they just represent the distance or the number of standard deviations from the mean. Okay, to begin, we're going to look at a problem that deals with US SAT scores, and look at these scary statistics for SAT scores in the US, math scores and reading scores over the years. Okay, now here's the situation we have. In this data set, let's say those are SAT scores for a particular group of applicants, and we are going to look at this and fill this in here. So SAT scores are represented by random variable x, which is normally distributed. We can see it here. And our mean, we can kind of approximate here, is about 1,400. And our variance is about 300 squared, so our standard deviation is about 300. Looking at that data, that's what we have here. Okay, so what is the variance? Well, the variance is 300 squared, which is 90,000. Okay, anyway, we're just kind of defining the normal distribution there. Now let's use that. So what is the z-score for an SAT score of 1,700? So here's that distribution here with our mean of 1,400, and we can see standard deviations of 300. It's going up by 300. So how do we standardize it? If we know we're looking for an SAT score of 1,700, which is right here, what will the z-score be? Well, I think that answer is probably obvious. We have a x value of 1,700, and it's exactly one standard deviation from the mean, so the z-score for that will be exactly 1. Okay, how about this one? What if we have an SAT score of 800? So think about where 800 is on here, and then can we normalize it? Can we give a z-score that matches that? Well, 800 is here, which again is exactly 1, 2, exactly 2 standard deviations back from the mean. So that means our z-score will be right here, -2. Okay, those are easy ones to start, right? Data isn't always exactly on these standard deviation values, but in this case that's what it was, so it's easy to get the z-score. So we're standardizing, that's easy, right? Okay, now let's try this. What is the z-score for an SAT score of 1,850? So think a little bit harder on this, but think about where it's going to be on here and then what it would represent on here. Well, here's 1,850. Now, if you thought about this carefully, you would have noticed that, again, the difference here is 300 because the standard deviation is 300, so here also. And half of 300 is 150. And that's what we see 1850 is. It's exactly 150 beyond 1700 or 1700. So it's halfway through this next standard deviation. Therefore, that x-score converts to this z-score, which is exactly 1.5. 1.5 standard deviations from the mean. How about this one here? Now we're looking at an SAT score of 1,025. A little bit tougher, but also it's going to be one of these ones where we can sort it out pretty quickly. So let's see if you can figure it out. Okay, 1,025 is about there. Now you're thinking, okay, we went back one standard deviation and a little bit more. How much more? Okay, to get to 1,025, this is another 75 back here. And what portion is 75 of a whole 300 standard deviation? Well, 75 is 1/4. So that means we must have gone 1 1/4, so minus 1.25. I hope you figured that one out. So there's kind of a pattern that's emerging here, the way we can get the z-score. And that's what I'm trying to lead you towards. So here's that last one we saw. Now I want you to think of this one as like this. Okay, to get that 1,025, I was thinking, well, how far is 1025 from the mean, right? Because the z value represents how far we are from the mean, how many standard deviations from the mean. So how far are we? Okay, we can subtract those two values, and we know then that we're negative 375 from the mean. Now, what can you do with this number and the standard deviation in order to find this value? Okay, I hope you thought about that for a moment and said, okay, well, I can divide it because I'm going back 375, and if I divide it by 300, it would tell me how many 300s go into here. And each time you have a 300 that goes into here, it represents one standard deviation, right? So when you divide those, you get that value, negative 1.25. We're saying how many standard deviations are within that move that we made. All right, so that's the process. I want you to think about that and try that for this one. What is the z-score? So try a similar approach. I hope you did. And let's see what we got. If we're talking about 1,638, so I'm going to say, okay, there's our our standard normal distribution, 1,638 minus 1,400. So again, I'm checking what's my distance from the mean. In this case, I'm a positive distance from mean, right? I'm 238 positive from the mean. And then I'm going to see, well, what portion of a standard deviation is that? Okay, so 238 divided by 300. That's going to be less than 1, right? So we're less than 1 standard deviation away from the mean. So I've taken my score, x score of 1,638, and I've standardized it, turned into a standard normal score, z-score, and that's 0.739. So that's about here. If we look back on our original data set, I put it here as well. 1,638 is about there, and it matches exactly what we found here, 0.79. See how it's in exactly the same location? Perfect. That means we standardized it perfectly. We got the right z-score. Now, I'm going to challenge you to go a little further with that. Looking at that last one and the setup we did for it, I want to ask you this. So based on the calculation we did here, suggest a general rule for calculating the z-score. So now I want to kind of like a formula. So z equals whatever. How do we get that z-score? And I want you to use x in it, the mean, mu is mean. We can use x bar also for mean, and the standard deviation. What will that formula look like? Think about what we did here. Write out the formula. Okay, I hope just by looking at this, you were able to come up with a formula, right? Or the way we find the z-score is we do our value minus the mean. That's what we did here, our value minus the mean to get that difference. And then we divide it by the standard deviation. And that tells us our z-score, how many standard deviations from the mean we are. So here's our formula. It's a key formula for calculating the z-score. Write that down. And now let's try it again. So find the z-score for an SAT score of 1057. So use this formula we just came up with. All right, check it here. We're going to subtract those, divide by 300. We have this z-score. Now let's double check that one on the graph. Okay, so we're looking for x values under SAT scores of 1057. So let's say you're looking for these x values less than 1057. So here's 1057, and we're looking for this area right here, right? And then over here, we just found out the z-score is negative 1.14, which is right here. Again, the locations match because we did a proper conversion, and that's a z-score of that. So here, if we were to write this, we're looking for a probability that z is less than that. See, here we use it using the original data, and here we do the calculation probability using the z-score. It should give you the same answer. That's what I want you to check on your calculator now. I'm going to solve it using this probability, and you go ahead and solve it using this probability. Let's see what we get. Okay. So like I said, I was punching in using the original values. So I have a mean of 1400, a standard deviation of 300, and I put here that. Okay, paste and calculate 0.126. I hope you got the same when you did it using the standardized curve. Okay, I hope you matched that. Okay, let's keep going. So we just learned how to standardize. So let's say we have a different example here. The weights of 1 liter water bottles the weights of 1 liter bottles of water are normally distributed as shown in the curve above. So now this data, I've put some context to it, and we are saying it represents weight of water bottles. So I put W for weight, normally distributed. Here's the mean, here's the variance. Okay, we're going to standardize that to this. Okay, 0 and 1 again. And the first question is this: what percent of bottles weigh over 1,035? Okay, so 1,035 would be somewhere here, right? Okay, So we're looking for W being greater than 1035. So using your calculator, don't standardize it, don't find a z-score, just use the original data and find this probability. Okay, hopefully you get an answer of this, 0.106. Now, question 2, we're going to take that, we're going to standardize that, so find the z-score that corresponds to that. And then use your normal CDF with the z-score and this curve, 0 and 1 as your values instead. Do you get the same result? Okay, the z-score, we're going to use that formula. The z-score is calculated and we get this z-score. So we're looking at 1.25 standard deviations above the mean. And when we look at this, when we went to 1035, that makes sense. 1.25 would be right here, and it's 1.25 right here. So this calculated on your calculator will give you the same probability exactly. It's important to know. Let's keep going. Okay, so there's our data. Let's try question 4 for this situation. The manufacturer will reject bottles that are in the bottom and top 10% of weighted bottles. So in other words, when you go to the bottom 10% or the top 10%, so the lightest bottles and the heaviest, they will reject them. They want their bottles to kind of all be clustered around the mean. Okay, what are the weights of rejected bottles? So where's the bottom 10% and where's the upper 10%? So on this curve, show the relevant areas we're going to be shading to calculate and then find the rejection weights. Try it yourself. Okay, so here is bottom 10%, here's top 10%. Okay, so you can calculate them separately or you can calculate it once and know that there's symmetry, which can help you solve other parts. Okay, so we're looking for, let's say here, the bottom 10% and over here, the top 10%. So we're going to do our inverse normal, right? Because when we know the area, we run an inverse normal CDF, inverse normal. Okay, so we're looking for weights under, and I'm putting some lower weight limit right here, and it equals 10%. So run your inverse normal. Tell me what you get. Okay, that should be 984.4. Great, so we know that anything is at weighing at 984.4 is or below is going to be rejected. Okay, how about the upper one? So run another probability like this. Right now we're looking for weights that are greater than some upper weight limit. And then 10% again. So run your inverse normal and you should get this, 1035.6. All right, so we know where the limits are that we reject. Great, let's try the next one. So given this distribution here, find the z-score and then the probability of each of these. Okay, that one, if you convert to z-score, you get 1.5, and the probability works out to 0.933. Notice here it shows it probability less than 13 from the original data, and also probability less than 1.5 for the standardized curve. And the probability is the same both ways. Okay, in B, you're looking for probability greater than 9. Again, find the z-score and then find the probability. Okay, here's your z-score calculation. We're negative 0.5 standard deviations below the mean, and calculated either way, you will get the same probability. Now try C. Okay, here we have two z-scores, the lower one, the upper one, and of course you could have punched that in your calculator to solve, but we're practicing z-scores as well. Using these z-scores, you have this probability. It works out to this, which is the same if you use the original values. Great. Now, what if you ask Siri, what is the meaning of life? We're getting pretty philosophical here. Let's check. Do we have an answer for this? The meaning of life is quite simply, and then it gets too blurry. We gotta get our eyes checked, because if our eyes were pretty good, we would have known the meaning of life right here. Okay, well, here's the meaning of life. Birth, all the stuff in between, and death. Pretty simple. Okay, maybe we should change our question. Instead of Siri, what's the meaning of life, we can just ask Siri, what's the mean? Okay, so we're going to do some problems now where either the mean or standard deviation or both are unknown, and we have to solve those. Instead of finding an area or a probability or something, we're going to find the mean. Okay, but to begin, we're going to do a problem that has the mean, but we're going to use an approach that's going to help us get to these ones where we have to solve the mean. So you'll see how this works in just a moment. Okay, so these problems have a little twist on them. Let's see what this one has here. It says sacks of potatoes with mean weight of 5 kilograms are packed by an automatic loader. In a test, it was found that 10% of bags were over 5.2 kilograms. Use this information to find the standard deviation. Yeah, notice the standard deviation was not given to us. So we know the mean is 5 though. So the mean is 5. We know that there are, let's see, 10% of bags are over 5.2. So here's 5.2 and 10% of bags are there. So this is kind of like different than what we've seen before. In the past, we've seen if we're given a value along here, we can use normal CDF to find the area. But in order to enter that in our calculator, we need to know the standard deviation. We don't have it. Also in the past, when we were given an area, we automatically thought inverse normal. And then we could find this location. But we already know that location, so we don't need to do inverse normal. So what's going on here? All right, well, we don't know the standard deviation. So how can we do it? Well, the only formula we know that includes the standard deviation and an area value, for example, is like the z-score formula, right? So let's take a look. We're going to find the z-score. But how can we find the z-score when we don't know the standard deviation, right? The z-score formula has standard deviation in it. So wait a minute. Oh, wait a minute. So, but we do know the area. And if we ran an inverse normal on a standardized normal curve, so imagine we took this curve and made it a standard normal with a mean of 0 and standard deviation of 1. So why don't you do that? Use an inverse normal, but use it as if this was a standardized normal curve, because the area is the same, right? The area will still be the top 10% there. So see what you get for your z-score doing that. Okay, so our z-score is 1.28. Again, you ran an inverse normal using 0 for mean and 1 for standard deviation. Gives you a z-score of 1.28. That means that this location has a z-score of 1.28. Okay, so now let's use our z-score formula. The z-score formula and plug in everything you know. Try it out. Okay, here's our z-score formula. We now know the z-score is 1.28, so this is replaced by 1.28. We know our value is 5.2, our mean is 5 back in our normal data set, and then there's our standard deviation, the only unknown. This can be solved. Try it. Okay, solving for sigma, or our standard deviation, we have 0.156 kilograms. All right, really interesting use of the standard normal distribution to help us solve this with the real distribution here. Okay, so that was kind of a basic one to start. Let's try one that's a little bit harder. So there's ones that look like this. Let me show you. A manufacturer does not know the mean and standard deviation. Whoa, now the mean and standard deviation are both unknown. Okay, so we do not know the mean and standard deviation of the diameters of ball bearings that she is producing. However, a sieving system rejects all ball bearings larger than 2.4 centimeters and those under 1.4 centimeters in diameter. It is found that 8% of ball bearings are rejected as too small and 5.5% as too big. What is the mean and standard deviation? Okay, so we're given some information about the upper end and the lower end. Okay, so let's mark that on here. We know, first of all, that when ball bearings are 1.8 centimeters in diameter, then that is, what was it? The lower end was, okay, 8%. So that was 8%, 0.08. Okay, and when ball bearings have a diameter of 2.4, then that is the upper, it says 5.5%, so 0.055. Okay, so that's what we know. We don't know mean, we don't know standard deviation, but this is all we know. So let's begin like we did last time. We know an area, we can use that to find the z-score. Maybe the z-score will be helpful. Let's try. So find the z-score for this area here. What would be the equivalent z-score for this value? Okay, that one is called. Okay, so what are z1 and z2? Let's check. Z1 calculated is negative 1.41 and Z2 calculated is 1.598. So now that we have the z-scores, can we do the z-score formulas? One formula for each. We're going to create one for this, one for this. Try it now. So the z-score formula for the first one is this. All right, here's our value minus the unknown mean over the unknown standard deviation equals that z-score we calculated. And the other formula for this one will be this. Okay, now we have two equations. So we have a system of equations. Hey, we always seem to come back to these. We have a system of equations with the same two unknown variables in each. So you can use any technique you want. substitution or elimination, and you can solve for the variables. I think in this one here, I'm going to use elimination. So I'm taking this first one, I multiplied by standard deviation, so now we have the standard deviation over here to get rid of the fraction. This can further be simplified into this. I took that mean and I moved it over to that side over here. Let me set up the other equation the same way. Okay, so first I multiplied by standard deviation, so it's here, and then I'm going to move the mean over there as well, like that. So now I have two equations that are set up in the same way, so I can do elimination. I'm going to put one equation there and one under it, and I'm going to subtract them from one another. If I subtract the bottom equation from the top one, the means will cancel. So I'm going to put minus here and subtract everything here. That minus that, let's see, is negative 0.6. This minus that is cancels. And then this minus this is this. Now divide by this number and we get a standard deviation of this. And then we can take that standard deviation and put it into, let's see, into one of these here and solve for our mean as well. So there's our standard deviation and our mean. It all began by creating a system of equations. Great. So now two problems, just like the two we just saw. Give them a try. Here's the first one where we, let's see, what do we know? Yeah, we know the mean and we know, let's see, and we know 12% of children have a certain height and we need to find the standard deviation. So give it a try. Okay, now check your work. We found the z-score first, or set up the z formula here with an unknown standard deviation. Then I'm going to set this up and find the z-score because we know 12% is the area. So using inverse normal, we get this z-score. That then goes in here. Solve, solve, solve for standard deviation, and it is 7.69. Hopefully you got there as well. One last one. This last one is going to be like the second problem we did, the one where you need to make a system of equations. So read this carefully and see if you can do it. If you can get through this one, you have reached, I guess, the toughest kind of problem in normal distribution. Well done. Let's check your work. Z-score at the bottom end and Z-score at the upper end. Okay, there's our area of 0.3, 30%, and there's our area of 0.2, 20%. There's the two z-scores we have. Okay, now the two formulas. So there's that one formula using the bottom z-score and the score of 108 marks. And then the other equation is this, using the 80.84 z-score and the 154 mark score. Okay, this time I think I'm going to do substitution just so we can see both techniques used. So here's one equation, here's the other. I'm going to solve the second one for mean, and then I'm going to substitute that into the first one here. So now see how this mean has been replaced by the mean I solved in the second equation right here. Solve this equation and you can get standard deviation. Oh, what happened here? Oh, that should say standard deviation. Let me change that. Fixed now. So that solving for standard deviation, we get this. Now taking that standard deviation, substituting in here, we can get the mean. And the mean is this value here. Great. Hey, if you were able to get those values, fantastic. Like I said, this is as tough as it gets in terms of what we do with normal distribution. So well done, and see you soon.